Yes, I'll record the talk, and so even if you have to go miss it, you can always come back. All right. So I'll be talking. So first of all, the reason I'm giving this talk is that I decided I'll be giving monthly talks about a random paper each month I'll be reading, and so this the first random paper that I happened to choose. So I guess Shanties ended up choosing for me, and so the paper itself is about counting, or maybe not precisely counting, but properties of the sequence of the amounts of topologies in a finite set. So we'll be looking at some finite set of some cardinality and trying to determine facts about the number of topologies on it. And so in this specific paper, which is by Kismas, and it's on archive 1503-08359, it's written, uh, there's a new technique developed to do that, to find properties using group actions. So first, let's review some stuff about group actions. I'll only be assuming that everybody listening is familiar with general topology and some basic group theory. So I'll review group actions. So a group action, so we always have a group action on some object, and we'll consider group actions on sets. So a group action is on some set, and we act by some group. So if you have a group G and a set X, a group action is just an homomorphism of the group into the automorphism group of X. And the reason we do this is because now, given some element of G, we can look at the value and at this homomorphism. Then we can, like, using this value, kind of scale elements of X by applying the function, because an automorphism of a set means a bijection from X to itself. And so when we have an element of a group G and a group action on some set X, then we can, like, form the element of X GX. And so this is going to be handy because we'll see some observations of how to have group actions on the set of topologies on a set. But for now, uh, some things we'll be using is orbits and stabilizers. And so when we have a group action of G on some set X, the stabilizer of this element X is just the set of all elements in G, such that G of X is X. And so I'll remind you, G of X was just, we take a group action, say rho, we take rho of G, this is bijection, X to X, and so that Gxx equals X is just notation for rho of G of X equals X. So basically this is the kernel of the, not really the kernel, but it's, right, I'm not going to go into kernel stuff, but it's just all the elements of G which fix X, and it turns out this is a subgroup. Right, and another thing that's useful is, so these are the stabilizers of elements, and besides stabilize, we also have the concept of an orbit of an element. And now the stabilizer was a subgroup of our group G, and an orbit of an element is going to be a subset of the set which the group action is happening on, and it's going to be just this set Gx as G goes through G. For the element X, this is the orbit of X, and also Gx. So we can use my cursor to this set, and we can kind of think about just, maybe let me draw an example, just in case anybody is not familiar with group actions. So a very natural setting, when we have a group actions, we can let's not use solids, let's just say we have 4 points, kind of arranged, let's make 5 points, kind of arranged like a kind of squarey cylinder like this. And so we can have its automorphism group act on this. So we can have the automorphism group of this act on this. So when we think of this as a set of 5 points, so P1 through P5, so it doesn't really matter what the points are, we can have the group action of the automorphism group on this set, and it's going to be a homomorphism from the automorphism group to the automorphism group, so we can just take the identity. And so now we can take some, so first of all, this is going to be S5, the automorphism group of this, because it's just an arbitrary set. And so we have 120 elements, and now the stabilizer, for example, of this point, so let's say this is P1, then the stabilizer of P1, so this is not a stab P1, this is going to be the set of all the permutations of these points which fix P1. And CT is going to be a subgroup as noted here, and it's going to be isomorphic to S4, because we have to fix P1, the bijection, but these 4 points can be moved around arbitrarily. And the orbit of P1 under this group action is going to be the whole space, because what the orbit is going to be just a set of applying all the possible permutations to P1 and seeing where it ends up. So we can apply the identity, it's going to end up here. We can apply any transposition, and then they're going to end up in all these points. So the orbit is the whole set. And so now we can look at the cardinalities in case everything's finite. If the group is finite and the set is finite, we can look at the cardinality of the orbit, and we can look at the index of the subgroup. And the index of the subgroup, I remind you, is the amount of left cosets of the subgroup. So we can take an index even if the subgroup isn't normal, which is in general not the case. And this turns out to be the same as the amount of right cosets. And for S4, this is going to be 5 in S4 and S5 because they're all of the same size and they're disjoint. So it tries to divide the order. So the index is going to be in the finite case the cardinality of G divided by this should say the index of the stabilizer of X. Sorry, divided by the cardinality of the stabilizer of X. And so 120 divided by 24, that's 5. And this theorem, the orbit stabilizer theorem, tells us that this is the amount of elements in the orbit. And so this is just a basic fact. I guess I have to erase this. This is just a basic fact of group action theory, that when we take the orbit of an element, this is going to have as many elements as the index of the stabilizer has. So yeah, this is a typo. This should say step X. I'm going to fix that later. Alright, so this is all just background information, group actions. Now let's fix some prime P because we're going to be looking at number theoretic properties of the sequence. And now we'll have to consider what P groups are, because in order to figure out number theoretic properties of the sequence of like, I'm going to define the sequence later, we'll be looking on actions of P groups on a set. So a P group is just a group in which every element has order P. So in particular, just to be clear, the identity element is always took to have order 1, so it's also power P. And we can characterize all these groups with a simple lemma in the finite case. So a group G is a finite, so a finite group G is a P group, if and only if the cardinality of G is a power of P. And so one direction is clear by Lagrange's theorem, because if the cardinality of G is a power of P, we know any element has order which divides the power of P, which the cardinality is, and has itself as a power of P. And now to reverse revision, we have to use something called the Cauchy theorem. And Cauchy's theorem states that when the cardinality of a group has some prime divisor, then there's an element of the group whose order is this prime divisor. So here this is written up, forward direction by Cauchy's theorem and backwards by Lagrange's theorem. So in the finite case, P groups look just like groups of order P to the K. An example of an infinite P group, which is not finite, an example of an infinite P group would be the Prüfer group, Z adjoint 1 over P modulo Z. So you can think about that if you want. So there are also, there's a huge theory behind P groups, and to go into it, we just need a little bit of P groups, and yeah. So we'll be only interested in finite P groups, so it's completely sufficient to just consider groups of cardinality order P. And so immediately we can now state the lemma which we're going to be using in order to derive some number theoretic properties of the sequence we'll be investigating. So for any set X with the P group G acting on it, we can say something about the cardinality of X mod P. And so in the future, we can use this lemma to take X to be a set of all the topologies in a finite set, and then we'll know that its cardinality is going to be this thing mod P. So what's this thing? This thing is the amount of all elements of X which are stabilized by all the elements. So who stabilizes the whole group G. So so this is the set. This is just all elements which are fixed by all elements of G. And we say that this theorem states that the cardinality of X is congruent to this modulo P, so the cardinality of this modulo P. And now intuitively why this holds is because anything which is going to be outside of the set inside X is going to have an orbit, and because G is a P group, the orbit is going to have, by the orbit stabilizer theorem, a power of P elements. And so the complement of this in X is going to have a multiple of powers of P. Hereby a power is going to be an actual power, so power P to the N with N greater 0, so a multiple of P. And we're going to have that the complement of this is going to be partitioned into orbits, and each orbit is going to have a multiple of p elements, and hence the complement of this in X is going to have a multiple of p elements. But in that case, we know that the cardinality of this plus the cardinality of the complement, which is a multiple of p, is the cardinality of this. So this plus a multiple of p is this, hence they equal modulo p. So here's this written out again. So we consider just call the set f, and again it suffices to show that the complement of f in X is a multiple of p. Oh, am I disconnecting? Did I disconnect? Oh, how long have I gone? Oh, all right. Okay, can you see my screen? I don't know, just disconnected. Internet issues, I guess. Right. Yes. All right. Yeah. Sorry. If anybody listening to the recording, I accidentally disconnected from the Discord where I'm sharing this. So let me continue. We're doing this proof of. Oh, actually, also one remark for anybody who has questions at any time. Please feel free to speak up. You won't be in the recording, but I'll repeat the question so everybody in the recording. Oh. Oh yeah. Sorry, I'm not reading chat. And Nikolai, let me see the question. Uh, so the question is. Yeah, it was a typo I pointed out later. So yeah, this x, it should be the stabilizer of x. Sorry. Uh, yeah, I'll fix it later, but I'll post the notes. All right. So let's come back to this theorem. So the way we can prove this is by calling this set f and then considering the complement and showing that the complement has order which is a multiple of p. Because if the complement has an order multiple of p, then the order of x is the order of this plus the order of this. So it's this plus a multiple of p, hence the equal modulo p. So in order to do that, we can partition the complement of f into the orbits of the elements. And we know that every orbit is going to have a multiple of p elements by the orbit stabilizer theorem, because we know that the orbit is the index of the stabilizer subgroup, but the stabilizer subgroup is not the trivial group. Oh, sorry, not the whole group, because otherwise it would be an element of f, right? These are all elements of X, such that their stabilizer is the whole group. And so if we have an other element in the complement of f, then their stabilizer is not the whole group, otherwise it would be an f. So in particular, the index of the stabilizer is not 1, and in particular because G is a p group, we know that it's a power of p itself, so it's a multiple of p in particular, so non-trivial power, and we know that it's the size of the orbit. So the orbit stabilizer theorem in this case tells us that the size of all orbits outside of the set is always a multiple of p of any given orbit. And it can also be checked that the orbits, they partition the complement. So yeah, this can be checked. This is done thing here, I believe. Well, yeah, they always partition the complement. Each of the orbits has a multiple of p elements, and hence the complement is a sum of the cardinalities of the orbits is a multiple of p. So this proves the theorem. So let's go on. We can now use this in topology once we define some group actions on the set of all topological spaces. So to do that, first note, if we have a group action on the set X by some group G, we can extend it to the group action of the power set. And we do this just by like this coset formation. So we map, so strictly speaking, this map phi G is the same map as mapping a subset of X to its image under G, or on the row of G, strictly speaking. And so this kind of like giving us an action of G on the power set of X. Now, given an element of this, an element of G, we can like act by this element of G on this set in the power set and get another set in power set. And for each element G, this is a bijection because multiplying by G, by elements of G, are all bijections. And we can check that this in fact defines a group action, the power set. And now we're going to be extending this, or restricting this to group actions on the set of all topological and Kolmogorov topological spaces, topologies, sorry, on X. And so just for notation, for any set, note by this the set of all topologies on X, and by this the set of all Kolmogorov topologies. So Kolmogorov, I remind you, a topology is Kolmogorov if any 2 points are topologically distinguishable. And what that means is that there's an open set containing one but not the other. And the reason we consider Kolmogorov but like not say Hausdorff is because anything which is higher than T1 is trivial. So if you have a finite topological space which is T1, then it's discrete. There's one thing which you can also consider. You can consider regular and normal spaces which are not Hausdorff. So usually T3 means regular Hausdorff and T4 normal Hausdorff. You can just drop the Hausdorffness condition. These are called regular and normal spaces, and you consider them. You can consider them and also count them. Yeah, you don't do that here in this paper. And yeah, so we know by mathfrak Tx set of all topologies on X, mathfrak T0 X set of all T0 topologies, and now take cardinalities just regular T of X and regular T of 0 of X. And yeah, so now what we can do, we can consider, so say we have a group action of a set of a group G on a set X, we can, using the observation here, extend it to a group action on the power set of X, and then it turns out that we can restrict it to a group action on the set of all topologies. So this is something that actually needs to be checked, but this is pretty routine to check. Again, you can do this in exercise if you want. So just to be clear, what we're doing, if you have some set X and a group action of G on X, we can get a group action induced by it on the set of all topologies on X, right? So now the elements of the set which the group G is acting on are topologies on X. So topologies here is literally the set of all open sets, so it's going to be a subset of the power set. Yeah, and we can do this with the set of all topologies and the set of all Kolmogorov topologies. But now note, now we've got a group action on the set of all topologies, and if we consider acting by p groups, we can get results like this. So we skip a little bit. So first, let's fix some notation. In a finite topological space, we can take the intersection of all open sets containing any given point, and it's going to be open because it's a finite intersection. And so we denote this set by OX. And the set of all OXs is noted by m tau for topology T. And it's a basis, and it's like a smallest basis, or in the paper, or in just literature, it's unfortunately named minimal basis, which, well, correct least basis would make more sense order theoretically, but these are like bases which are contained in any other basis are known as minimal basis, and there's always a unique one in the finite case, which is this one. But anyways, this is going beyond. You just have the collection of all these intersections of all open set containing points are bases known as m tau of any finite topological space. Oh, yeah, I guess finite topological space. So now we finally come to the first theorem actually considering any topology, namely that the amount of topological spaces on p to the k elements, remind you, we fixed the prime p, is congruent to k plus 1 modulo p. So this is kind of random if you think about it just out of context, but we can explain it with group actions. But so, for example, this would say that the amount of topologies in a set with 9 elements is going to be 3 modulo 3, so it's going to be congruent to 0 modulo 3, so it's going to be multiple of 3. And that's kind of interesting, and there's going to be a lot of results like this we're going to see. So the way we do this, we consider a group action on the set of all topologies of the set of cardinality p to the k by a p group, and then we can use the lemma we got there that the set f, or we didn't note it f up there, but the set of all the elements fixed by all the elements of the group is congruent, the cardinality of it is congruent to the cardinality of the set of all topologies and p to the k elements modulo p, if you're acting on the set of all topologies via p group. And such an action by a p group we can get by acting on mathfrak T of X for some X with p to the k elements by a p group. So the way we do this, the way we get this action, we consider X itself, so the space we're going to be forming the topologies on, to be the cyclic group of order p to the k. And we consider it acting on itself by left multiplication, and then we take the induced action on the set of all topologies in X, as we did in the previous slide. We defined that we can extend the group action. And so now we have the group action. So I actually, just now, that Cp to the k is just notation for the cyclic group. C is kind of common here. And yeah, so, right, so let's continue. We get this induced action on the set of all topologies on X, and now if we determine the cardinality of this set, we know that the cardinality of this set, so T of X, is congruent to it modulo P by the lemma on the previous slide. And so the way we do this is we determine an explicit bijection between this set and the set of all subgroups of C to the P to the K, Cp to the K. And the way we do this is um, we map an element of this set to O0 into the topology. So an element of this set is going to be a topology, and so it's going to have its own O0. 0 is just an element of the underlying set because the underlying set was a group, and 0 denotes the identity element here. And the inverse mapping maps the subgroup to the topology generated by all the left cosets. And so one can show that this is actually a bijection, namely if we have some element of this topology, then m tau partitions tau into pairwise econumerous blocks. So it's going to be making it into a group just fine. So you can check this bijection works. As said here, we associate O0, and to a subgroup of Cp(k), we associate a topology here by taking all the left cosets and generating the subgroup. And so now we know that the canality of this set F is Cp to the K, the amount of subgroups of Cp to the K, sorry. And there are K plus 1 subgroups of Cp to the K. That's just a group theoretic fact, you can check that. And so what we've shown is that because the K plus 1 subgroups of Cp to the K, this is the amount of elements of F by this calculation where we determine a bijection. And this is congruent to the amount of topologies on X modulo P by the lemma before. And X had P to the K elements, so T of P to the K is congruent to K plus 1 modulo P. So it's kind of an interesting fact. And now we can continue using this method to figure out other facts, like we can show that the amount of Kolmogorov topologies on two sets, if you have two numbers k and m, two positive integers k and m, which are congruent modulo p minus 1, then the amount of Kolmogorov topologies on either of them is congruent modulo p. And so we do this in a similar fashion. We define a p group action, but now we do it on this set, we do it on the set X, which is the disjoint union Cp disjoint union n, whereby n is some set with n elements. Sorry, what is n? So in order to show this, we want to kind of show that when the input is the same modulo p minus 1, the output is the same modulo p. And so for positive integers. And so it suffices to show that we can always have the step from n plus 1 to n plus p. Right? We just step up p minus 1, and we can always do this for all natural n. So I take natural to include 0. In that case, this is true, because if the k and m are congruent in modulo p minus 1, we can always like step up, taking n be the lower one of those, and then stepping up p minus 1 and continuing until we get to the upper one, and then they're going to be congruent modulo p because of this. Right, so let's return to the group action. We take n, capital N, with some set of cardinality n, and X is disjoint union, and we act by the p group Cp on X. We're defining the following group action. We take some element small x of capital X and act by some element g unit by defining gx be g plus x if x is in Cp, because if x is in Cp, we can we're acting by Cp on Cp, so we can just add, and we fix all elements in n. And so we've got this group action by a p group on the set, and now we can take T0 of the set, math frac T0, and extend the group action. And then apply, because this is a p group, the lemma of slide 4, theorem of slide 4. And so if you do that, it now suffices to determine this set. So now we've got Cp acting on the set of all topologies on X, a Kolmogorov topologies on X. And X is the disjoint union of Cp and n, and we act pointwisely like this. And now we need to determine this set F or its cardinality in order to determine this congruence modulo P. And so we need to determine the amount of Kolmogorov topologies such that they are fixed by all elements of Cp under this action. Sorry, G should be Cp here. And so, right, we now want to show that this thing is T0 of n plus 1. And so the way we can do this is, this follows kind of because whenever we have one element of Cp, and we know kind of the topology locally around it, we know the topology around the whole of Cp. But we can give an explicit projection, which is kind of identifying one element in Cp, so just taking some element of Cpy, and taking the whole of n, taking a topology on that, and then mapping it back with appropriate projection. And so actually it is better to do in the other direction. So we take a topology on T0x, on X, and then we restrict it to the set Y, whereby Y we just restricted the whole of N and one single element in CP. Now we get the Kolmogorov topology on that, and so we associate it to T0x, so something in T0x, something in T0y. And so we can do this bijectively because the whole of the topology in CP is determined locally by elements of CP, and we're going to see this a little bit later in more detail. It's kind of just a calculation. And so we get the bijection, and now we know that the canality of F is just T0 of n plus 1, because we have a bijection with T0y, and y has n plus 1 elements. And so now we've shown this theorem by determining the canality of F, and by using that lemma, that theorem, and then getting this result, and hence this result. So actually this is kind of a more classical theorem, which goes back to Borovich, I think. Actually, I'm not sure if it goes back to Borovich, but Borovich is kind of known, it seems, for this thing. And yeah, this is just proving this. So classically, this theorem is proved by using like very explicit combinatorial computations with Stirling numbers and all this stuff. But here we can just use the elegant group actions and acting by p groups, and we get this result, which is kind of neat. So actually, one thing I want to remark on is that, so as you see, the theorem is stated only for positive integers, but it really seems that the theorem is true for all naturals, and I couldn't track down the reference, but that just seems to be the case. So yeah, I don't know, maybe if somebody finds a reference, that'd be great. So let's continue. So here's another, but I guess it's a corollary that T0 of p to the k is congruent to 1 modulo p. So the reason that is of course because p to the k is congruent to 1 modulo p minus 1. That's just number theory. We kind of can commute with powers, and we get just 1 to the k, which is 1. And T0 of 1 is obviously 1. It's just the only Kolmogorov topology on a singleton. There's only one topology, and Kolmogorov topology on a singleton, and so there's one topology, that's Kolmogorov. And so this just follows because p to the k is congruent to 1, and hence T0 of 1 is congruent to 0 of p to the k, but T0 of 1 is 1. So now let's go on. We're going to need some more machinery now. Namely, we need to use the fact that when we have a group action of a group G on a set X, finite set X, and we extend it to T of X, then the set of all the topologies tau on X, which are fixed by all the elements of G, this F that we used, is precisely the set of all the topologies whose minimal basis M tau is fixed by all G, so it's kind of invariant. So G M tau is just this. And so this is proved straightforwardly. So this is if and only if. So let's go the forward direction. Suppose that G tau is tau, so G is in this set, tau is in this set F for all group elements G. Now we need to show that G M tau is M tau, so GO, so every element of M tau is the form GO for some M tau, and that GO is always in M tau. So first let's show that GO is in M tau. So we can show that GOX is OGX. By the following computation, we know that G inverse OGX is contained in G inverse GOX. That's just OX. And because of symmetry, this shows that thing. And actually, sorry, I'm not sure whether symmetry is involved, but this is just a direct computation. And now, because multiplication by G is a bijection, it follows that every OX can be obtained like this. I guess it doesn't even need it as really a bijection. It just suffices to show that G inverse OGX is OX. Alright, so this is the forward direction. I mean, it's really all computation. It's fine if I'm kind of rushing this and you're not following, but backwards direction that if G M tau is M tau for all G and G, that G tau is tau for all G and G, we just write any open set in tau as the union of OXs for X and U, which can be shown. So OX is a basis, so this works out. So the set M tau is a basis, so this works out. And then we can compute multiplication. So because this is formation of cosets, we can compute union with multiplication by G on the left. I guess we can only multiply on the left. And then we use the GOX is something in M tau because G M tau is M tau. And so we have a union of like open sets. And subjectivity follows similarly because we can check G inverse U. and that's U, and that's open. So it follows. So sorry, it's might have been kind of messy because it's computation, but all we're doing, we're just giving another characterization of when it is the case that the topology tau is fixed by all uh, the elements of a group G, which is acting on the underlying set of where the topology is. Right. So now we can use this to define a very fundamental thing. It's going to be this sequence of integers, namely for any natural n, there is a unique integer case satisfying that for all primes q, this congruence holds. So far we had kind of more multiplicative properties of the sequence, so like the amount of topologies on p to the k, p times p times p, kind of multiplicative, and now we can kind of see what happens if you deviate from some natural by some prime amount q, and we can see that this is always fixed modulo q. So for example, if you take n equals 0, we know that t of q is always going to be congruent to something fixed modulo q, and we know it's going to be 2 by the previous theorem. Actually, this is how we start the proof. We consider the case n equals greater than 0, because for n equals 0, k equals 2 suffices, because t of q is t of q to the 1, which is congruent to 1 plus 1 modulo q, as shown in like the first theorem we've proven. And yeah, so let's continue with the proof. It suffices to consider n greater than 0. And so let's again take this set X, which is the disjoint union CP with n, where n is a set with n elements. Oh, sorry, I think this should say CQ. No, couple typos. And we define this action and kind of get the action that's induced on mathfrak Tx. And now we can consider this set, and all we need to show is that this set of all the fixed topologies is kind of independent of P. Because if it's independent of P, so actually it should be Q all along, but whatever. If it's independent of Q, then we know that no matter which Q we take, this is always going to be congruent to K modulo Q, because we're acting by a Q group, I guess P group. P is Q here. So how do we show that this is independent of P? So I'll just stick with P, even though it's a typo, but let's use P. So we do this by again noting that inside of CP, all the topology is kind of determined by very locally by one element. So we can, for example, take C1, and if we know sorry, this is so many typos. I'm sorry. This should be 1, not C1. If you take 1, then the topology is just determined by O1. So the reason that is if we know O1, we know that x minus 1 O1 is going to be OX just by direct computation. And so we know everything, all the topology inside of CP. And this allows to give us a direct projection. And further, we also know that O of something inside N is going to stick inside N also by direct computation. I'm not really going into much details here. It's all just the same technique, and we just apply it here. And the uniqueness here, that's a good exercise. It's kind of clear to show if you look at the statement. So right, let's continue. Basically done. So now we've got all these technical results, and we can kind of see them appear in practice. So actually here, let me note that the sequence here we note by Kn, that we just proved is well defined. And these are not powers, these are footnotes. Now we can look at some values here, and there's some things to be observed. For example, we can take like t of, so let's look at t of n. Let's take n equals 1 and q equals 3. So in that case, this should be q. In that case, we have that t of 3 plus 1 is congruent to k of n. So k of 1 modulo 3. So k of 1 is 7. So t of 3 plus 1, so t of 4, is congruent to 7 modulo 3. So t of 4 is congruent to 7 modulo 3. So to 1 modulo 3. And we can do this by adding the digits, that's 13, so yeah, that works out. So you can kind of play around, and here's a nice exercise to prove that TO of n is odd for all natural n. You can just do that using the results we've seen. And so yeah. And so just to finish up the talk, these results didn't really appear into the paper, but they're kind of interesting and decided to feature them here. So a lot of stuff goes back to paper by Erne in like I think the 60s or 70s. And so there he proved more analytic results with again hard computations. But if you didn't know it, by Z the amount of connected topologies on a set of cardinality n is at zero, the amount of connected Kolmogorov topologies, what turns out is that asymptotically we have that amount of topologies, connected topologies, Kolmogorov topologies, and Kolmogorov connected topologies is going to be roughly the same. So as we take larger and larger numbers, the amount of like topologies which are Kolmogorov or topologies which are connected or just topologies on a set of cardinality n, where n is the number you're taking, is going to be roughly the same. And so formally you can describe this to these limits. And so actually this is an equivalence relation, so we can also say that t is approximately t0 and stuff like that, asymptotically equal. So just another nice result. So we can, so we've seen that t0 is periodic modular p with period p minus 1, and actually t modular p is also periodic, but now with period p to the p minus 1. And so Borovich proves this. And yeah, so that's just a nice result to know. So kind of the amount of topologies on a finite set is always periodic modular p. Modular p to the p minus 1. And for Kolmogorov, it's modular p. No, sorry. It's periodic modular p when you consider the sequence modular p. It's just the period is p minus 1 for Kolmogorov ones, and p to the p minus 1 for regular ones. And here's just another nice result about the sequence kn that we have that amount of, well, we have this equation, and then it follows because of this, that this limit is this. Right, so actually this should be it. I'm not sure. It's kind of short, but I guess I planned it kind of short. It's a very computational paper, so let me stop the recording. And actually, before I stop the recording, does anybody have any questions? Oh, let me see the chat. No, well, we can talk about this later. Right. So yeah, thank you for listening. I'll stop recording.